Thank you all for coming today to our colloquium. Just the upcoming colloquia next week, we have Elisa Quintana is going to talk about formation and habitability of planets in binary star systems. And the week after that, Dr. Barry Bloomberg, former head of the NASA Astrobiology Institute, Nobel laureate, is going to give a colloquium on a topic of his choosing. And today we have Ross Beyer. Ross got his BS in astronomy and in physics in 1998 from the University of Illinois, then a PhD in planetary science in 2004 from the University of Arizona. Spent 2 years as a NASA postdoctoral fellow before joining the Carl Sagan Center here at the SETI Institute in 2007. Ross is interested in Mars, has performed geophysical modeling of diapirism on Mars and other terrestrial planets. And he works a lot on quantitative analysis of meter-scale topography using remote sensing data, which work has been used a lot for landing site selections for the various Mars missions. Ross is also interested in layering in Valles Marineris, and I'm sure we'll hear a lot about that today. Ross is also a member of the participating scientist on the HIRISE, the really high-resolution camera on Mars Reconnaissance Orbiter.
Thank you, Josh. As a consequence of my being a team member on HIRISE, most of the images I'm going to show you today are images from HIRISE. And if you're interested in examining those images in any greater detail, you can find more information on them by going to URLs that look like this: hirise.lpl.arizona.edu/the observation ID. And all the images I'm going to show you will have a little observation ID. And if they go by too quickly, just let me know, and I'd be happy to send you a copy of this as a PDF. So let me also first apologize to you for giving you two talks in the space of one colloquium. These two topics, Martian strata and slope streaks, are disparate. They don't necessarily have anything to do with each other, except for the fact they're both on Mars. But I'm interested in both of them, and I wanted to talk to you about both of them today. But before I do that, I will talk about just the instrument. This is an artist's rendition of the MRO spacecraft. It's one of the biggest spacecraft in orbit around Mars today, but size isn't necessarily that important. The size of the main dish there is about over 2 meters in diameter, so it's pretty big. HIRISE itself is the biggest tube on the nadir deck here. This is HIRISE, and it's about 50 centimeters in diameter, and as far as a telescope goes, it's an F-24 for those of you that are telescope people. But optics notwithstanding, the business end of HIRISE is this, the focal plane array. Now, on most cameras that you have, perhaps on your cameras, on your cell phones, or on cameras that you use to take pictures when you go on vacation, those cameras have a square CCD in them at the back of the optics, a two-dimensional array of pixels that take an image. But unlike those kinds of cameras, the cameras that we are sending to other planets these days are line scanners, which means that instead of a square array of pixels, they're a simple line of pixels. And we build up an image by spacecraft motion and kind of dragging that line of pixels across the ground as the spacecraft orbits. And so we get these long noodles. And that's, of course, what HIRISE does, but instead of a single array of pixels, a single CCD line array, we have 14 on our focal plane, and that means that each one of these CCD arrays is about 2,000 pixels wide, which means that when we take an image and we have all of these CCDs on, we get an image that's 20,000 pixels wide at about 30 centimeters per pixel, which means that we end up getting about a 6 kilometer wide swath of Mars at about 25 centimeters per pixel, and it's really quite impressive, as I hope to demonstrate to you. Now, the other thing is that in addition to this kind of wide array of what we call red CCDs, or kind of open bandpass CCDs, we also have a pair of blue-green and near-infrared CCDs that are stacked above and below, so that when those are on, we get this wide swath that's quote-unquote black and white, although it's kind of in this red bandpass. We can also get color down the middle, and I'll show you examples of that as I go forward. So let's go ahead and jump right to the first topic, which is strata. And there's great layering and strata exposed everywhere on the surface of Mars. I'm not going to be able to get anywhere near about talking about all of it. There's great layering in polar layer deposits, in crater deposits, really almost everywhere we look. So instead I'm going to just focus narrowly on strata exposed in the Valles Marineris, which is the Grand Canyon of Mars. Although if Valles Marineris were on the Earth, it would stretch from New York to San Francisco, and our Grand Canyon would be a very small tributary valley in it. So let's go ahead and start. And what I'm going to show you is really just kind of a whirlwind tour of the various kinds of strata exposed in the Valles Marineris, just to give you a flavor. So these are high-rise images of what is called the wall rock layers. Now, unlike the Grand Canyon in Arizona, which you may or may not be familiar with, I hope you are, the strata in the upper layers of the Grand Canyon are sedimentary. They're limestones and sandstones. But we're reasonably certain that the layers in the wall rock of Valles Marineris are probably not mostly sedimentary. These observations, previous researchers from previous spacecraft have proposed that perhaps mostly they were volcanic layers, basaltic volcanic layers. And these high-rise images show pretty good examples of that. There's very regular layering, which corresponds to the way that thick stacks of lava erode and provide their exposures. Although it's also quite possible that there could be interspersed layers of dense basaltic lava and sedimentary units. In other places in Valles Marineris, so I'll show you an example of our color products, and this is one of them here on the bottom right. Up in the upper right-hand side, you can see there's a zoomed-out version of a unit in Coprates Chasma. And near the top of that stack, I hope you can see there's this dark layer that you can see in the low-res version. And I wrote a paper in 2005 indicating that since this layer was dark, even on this sunlit slope, and other reasons that it was resistant, that perhaps this layer was a volcanic layer, perhaps the last thickest one that was laid down at the top of the sequence. When we got this high-rise image of that area, I noticed that you can really resolve the rocks and the boulders that are eroding out of that layer. And I thought to myself, well, maybe this isn't really dark, and I don't know if you can see this, but it may be that the boulders that are eroding out of that layer are big enough that the shadows shine upslope, and that this isn't really dark, it's just that the shadows are on the ground and we can see shadows at the lower resolution. That's what's tricking us into thinking that it's actually dark. However, once we got our color processing together, you can see down in the lower right hand here that these units actually are slightly bluer than the dust, which gives me a warm fuzzy that perhaps they are in fact a mafic layer that's outcropping and shedding talus downslope. Other units, on the floor of Valles Marineris, there are an abundance of light tone units within the chasmata. I'm not going to be able to show anywhere near all of those. These are just some examples in Candor Chasma. And you can see that these light tone units are interbedded with more resistant units that form little cliffs and drop talus and boulders, but otherwise are pretty ubiquitous. And there are lanes here in between these light tone units that we've seen before, again from lower resolution orbiters, and it's been proposed and I believe mostly confirmed by HIRISE that these are just kind of where dark dust and talus from these other units are laying. It's not that these layers here or here are actually are not structurally bright and dark and bright and dark. It's really a big mass of light tone stuff, and just simply in the crevices the dark stuff is accumulated. In these units also you can see a fair amount of folding, and there's a big fault that runs along here, and you can see displacement along the faults in a number of places. What I'm going to show you next is a zoomed out view. This is from another instrument on MRO. This is from the context imager, which provides us a 30-kilometer wide swath at 6 meters per pixel, which is fabulous. And the red and blue footprints are where high-rise stereo pairs are. And the white outline here on the right shows you the view that I'm going to show you next, which is the region of this DEM. So when we have two images that are looking at a surface from different angles, HIRISE can construct this DTM, this digital terrain model, from that stereo pair. And these two images have a 24-degree angle between them, which is the stereo convergence. Of course, there are artifacts near the edges. It's not very well controlled. That's to be expected. But the fabulous thing about this is that this area, as you can see, is about 6 kilometers wide by 7 kilometers tall, and the mesh that has built this has a 1 meter per post spacing, with a resolution of about a third of a meter vertically. And so the amount of detail in this is tremendous, and we're zoomed way out so you can see the whole swath. This DEM was made by the USGS and FlexApp, and is partially as an advertisement. Hopefully, in the next 6 months or so, we'll be getting the ability to make DEMs like this ourselves here at SETI and at Ames, which will be very exciting. But at any rate, getting back to kind of the science, I won't have anywhere near the amount of time to talk about that either. There's a lot of work being done. Chris Akubo on the HIRISE team is working on this area. And as you can see, it's even from this zoomed out DEM, it's a broad valley. There are a number of conformable 5 to 100 meter thick beds of these light toned units. There's a lot of disrupted bedding. And there are a number of, as you can see, these little hills dotted all over the place, capped with an unconformable dark layer. Now, whether that unconformable dark layer is just simply the last remains of a dark layer that was once ubiquitous across this area, or whether those unconformable dark layers are hydrothermally altered units is a question that Chris is currently pursuing. And again, by way of an advertisement, here's another view of that DEM, kind of from a more oblique angle. This is what that surface might really look if you were standing on one of those knobs. And just to give you an idea of the scale, again, the thickness of this is about 30 meters thick, and these guys are about 200 to 300 meters in diameter.
Is there a vertical exaggeration on that?
No, there is no vertical exaggeration on this DEM. That's how it would look.
What's the blue stuff?
Okay, so let me go back. Like I said, there's a color strip that runs through the middle of our image, and you can see it here, I hope. There's kind of the color swath through the middle. And here again is the boundary. There's the boundary of the color swath on each side. You can see it up there on the hill, and it comes down. So this is a false color composite from the infrared and blue-green channels. Since we only kind of have 3 points, doing a rigorous spectral analysis probably is not warranted. But basically, what we can do is, when colors are mapped out, they can be corresponded with spectral units seen in CRISM at much lower resolution. And so there's a pretty good correspondence between, you can see units in CRISM data and then look at those units, and they have a good correspondence to color units that we can see in our color strip, and you can get a much better idea of what their boundaries and shapes and terrains are in the high-rise images. And so the blue stuff is talus and probably mafic dust. And again, you can see this unconformable dark layer on the caps of each of these little mounds, which is fascinating. Of course, with DEMs like this, you can get, not only can you map in 3 dimensions on the surface, but you can also do 3-point solutions, and you can measure points along the edge of this contact in 3 dimensions and make best fit planes through those and find what orientations the layers in the bedding are, and get not only a 3-dimensional picture of the surface, but also at depth of how the layers are stacked and folded and tilted to get a good idea of what the geologic history of regions like this and others are like. So it's fascinating work, and you should be seeing a lot more results from DEMs and that sort of thing from HIRISE and CTX in the future. Moving on, there's no shortage of layering to be seen. At the western end of Valles Marineris, not only do we see layering in the walls and in the floor units, here's an image of a place called Oudemans Crater, which is, again, to the west of Valles Marineris. And in this zoomed-out CTX image on the right, the crater rim is beyond the bounds of this image. But you can see the central peak here and a unit of light-toned rocks that kind of surround it. And when we zoom in with HIRISE here on the left, you can see that those light-toned layers are fractured and disrupted, most likely as a consequence of their being exposed as a cause of the impact. So to some extent, to some depth, there's also layering beneath the floor, which is fascinating. So also there are a number of mesas in the Valles Marineris. These mesas and interior units are fascinating in the sense that in some cases they are as tall as the Valles Marineris is deep, which is at its deepest point is about 10 kilometers from the plateau above to the floor. And these mesas often stand 5 to 9 kilometers tall and display a variety of layering which is different from the layering that we see in the wall rocks that I showed you at the beginning. This image here on the left, the inset here above with the colors is some work from Mangold et al., which results from the omega spectrometer, and the orange units there are where they see a signature of kieserite, which is a monohydrated sulfate with magnesium, which is most likely a product of hydrothermal alteration. And it often corresponds pretty well to light-toned units, although not exactly. This image on the right is from the mound in Ganges Chasma, Ganges Mensa. And here, again, I want to show you that that the layering here, although at first blush it looks like it's a light, dark, again, the dark quote-unquote layers that you see are not actual structural layers. They're just where dark sand and talus have accumulated in kind of the stair-step treads of this lighter tone unit as it has eroded. And there's some remnants here in the middle of this frame. You can see a little dark oval that's the remnant of probably a dark mantle that overlaid this unit before it started eroding heavily and displayed this slope. In other places, again, more light tone units, but have a very different character. These units also have sulfate signatures in omega and also in chrism as well. And here in Juventai Chasma on the left, you can see that this texture is mostly a massive texture, although there is some kind of layering of bedding over here. And this texture you can also see is kind of scalloped, and it's not clear to us whether this scalloping is purely an effect of the wind erosion that has eroded this unit back, or whether these are the results of joints in the pre-existing rock that have been armored by hydrothermal alteration. And then as the unit erodes, the armored joints kind of stick up in this network. And again, this is on the right, Ganges Mensa Mound, down here on the foot of it. Again, this unit is very different looking in structure and exposure than the one that we just saw in the previous slide. So there's lots of different light tone lithologies. Finally, there's also layering not only in the walls, on the floor, probably underneath the floor, in these mesas in the Valles Marineris, but also on the plains above the Valles Marineris. So kind of, in the areas where, if you were at Grand Canyon, where Grand Canyon Village is, that kind of area up on top. There's also layering. And what's interesting about this layering that we found with HIRISE is that this layering actually does have different colors in it, unlike the layering which I showed you inside the Valles Marineris. These different units actually do have some different tonalities and different colors, which indicates probably a difference in sedimentary units. And also in these units, this is some work by Kathy Weitz and folks on the HIRISE team. These units seem to repeat. If you look at them very closely, there are packets of layers that repeat several times. There's this kind of a blocky unit that is here, and you can see it again here and there. And these kind of stacks kind of repeat. So that may be telling us something about seasonal processes or repeatable yearly processes that build up these layers on the chasma rims. But we don't know why they're up there. So there's certainly lots of research to be done with strata and the Valles Marineris. So just a short summary of strata and units that I've very quickly gone through with you. Inside Valles Marineris, not including the wall rock layering, there are two broad categories of lithologies. There's the blocky resistant units that produce debris aprons and form steeper slopes, and light tone units, which are less resistant to erosion. And these light tone layers vary a lot in morphology, as I hope I've just demonstrated to you, and are largely free of craters. Now, in a traditional context, this might make you think that perhaps those units are very young. But that's not true. The truth is that these units are eroding very quickly, and so what they have, their freedom from craters indicates that they have a very low crater retention age, which means that these units are probably eroding faster than new impacts can impact on top of them. So the units are very old. It's just they were once a lot bigger and did have craters on top of them. But the erosion, those units are being worn away, is moving faster, faster from Mars, of course, which is very terribly slow. Is making those surfaces eroded and fresher, and that's why they don't appear to have as many craters, although they are, in fact, most likely old. And finally, just a word of not necessarily a warning, but what a lot of people have done with Viking era data and Mach era data with a lot of these units in Valles Marineris is try to find one answer that tells you where all the light tone stuff came from. And I hope, again, that I've demonstrated to you that there are so many different lithologies and outcrops. There are a lot of different ways that you could get those kinds of units, and that not all light tone layers in Valles Marineris or in fact on Mars come from the exact same process. There are probably several of them that are creating light tone units. All right, so that's all that I'm going to talk about for strata. I'd be happy to answer questions.
Yeah, just
sure,
a question. What about the time scales? You say that it's faster than erosion. More nice to know it.
If we had very good radiocarbon dating on the surface, I'd be happy to answer that question, but we don't. So I can't really give you a satisfactory answer other than in this relative sense that, and of course the cratering flux at Mars was high during early bombardment and has really tailed off. So it's not a uniform rain of craters through time. It's sporadic. So it may well be that these units were placed early on. There was a lot of cratering at the beginning, and perhaps cratering has tailed off and has been nothing. And for the 3 billion years or 3.9 billion years between now and heavy bombardment, these things have just been steadily eroding, and not that many craters have been impacted at all. Or it may be that there were periods of repeated impacts, and these have only really started eroding in force in the last billion years. I don't know. I can't really answer that question. We don't have that kind of data.
Ross, while there might be a lot of explanations for different types of layering within the Valles Marineris, the plateau layering, could you count that as there would be one explanation for just plateau layering that you're seeing, or is there a lot of variation?
I see.
Prism sees a lot of opal and silicate in those layers. It's quite distinctive. Could it be that plateau layering had one explanation?
It could be, and these kind of different categories are very similar. I'll go back here and show you this. This layering that we see is observed in a couple of places around the rims of Valles Marineris, and when we do see it, although not identical in, as I mentioned here, there are these kind of identifiable packets that you can replace, but it does look like there's similar coloration, and so they may all have, those particular units may all have come from a very similar process. But it is unlikely that these layers were laid down in a process similar to those that we see in the interior. Yeah, that's absolutely correct. All right, so now I'm going to go and talk about something completely different, which are slope streaks. And let me give while strata and Valles Marineris is a relatively straightforward topic, for those of you that aren't familiar with Mars studies, I will give a short introduction to slope streaks, and that is that they're streaks that we see on slopes. I'll try and be a little more detailed, but that's essentially it. In places on Mars where there's a thick dust cover, a high albedo usually, we see on slopes these streaks. Now, there's a history to these. These have been seen all the way back from the 70s, and Viking Orbiter has had some observations of them, although since they were usually pretty small, Viking Orbiters kind of saw them as little streaks, and some of the high-res Viking Orbiter stuff resolved them a little better. The Mach camera in the late 90s and through till just a few years ago, or last year, I guess, when it finally went off, did a lot of observing the slope streaks. And the Mach view was one very similar to this. This is a high-rise image, but zoomed out. And you see these streaks on surfaces, on the slope surfaces. They have a variety of albedos. Usually they are darker toned than the surrounding surface, although that's not strictly true. And I'll talk a little bit about bright slope streaks at the end of the talk. You can see they have different tones. But Mach really couldn't distinguish what they were. As far as Mach, for the most part, observations from Mach and papers written on it show that these are just dark streaks. They couldn't necessarily identify any topography. So for all the world, they look like someone took a spray can and just sprayed on the surface. Although there is a notable exception. There is a Phillips et al. Paper last fall where we did find an exceptionally big one that we did see some topography in. And I'll show you that. I'll show you the high-rise version of that later. But so because there was no observation of relief in the Mach images, it was difficult to really say what was happening. And so there's a variety of dry models, a variety of wet models to explain how these slope streaks could form. Now, the other observation is that Mach saw these form in a relatively short time period, and so is high-rise. The shortest time period between two, so we can image a hill with slope streaks or without, and another image, the closest I believe was 20 days later, a new slope streak had formed on that surface. So these things are forming, in addition to forming historically, are also forming right now on Mars today. But what I'm going to show you is a variety of high-rise images that will hopefully prove to you the following bottom two items, which is that indeed slope streaks do have relief, and that they are part of a continuum of active mass wasting features that span a variety of scales. So let me take a look, show you a first high-rise image of these slope streaks. Now, what you can see, I hope, are a couple of things. There's it's high at the top of the image, and it slopes down to the bottom at the bottom of the image. The dust cover around, which you may not be able to see from the back, it may just look fuzzy for those of you in the back row, but those of you in the front can see that on this surrounding dust cover, there's a very fine network of reticulate ridges that look for all the world like the effect of a star dune pattern, kind of an isotropic distribution of little crests that are linked together in the dust. Now, what we can see in the streaks that we can see with HIRISE that you can't see with MOC are the fact that MOC, zoomed out, might just see this one or this set of slope streaks here that are notified by their darker tone here on this image. But HIRISE can show you that there are a ton of other slope streaks on this surface, just that they aren't dark. And we think that they aren't dark because they aren't dark anymore, that this is an evolutionary process, that they start out dark and then they fade away. And you can see these others have these incised sides. They look a lot like avalanche scars. And that's, of course, what the dark ones look like as well. It's just that they're dark on their floors and not the same albedo as the surroundings. These streaks reveal topography underneath, which is usually a little sharper in the slope streaks, indicating, again, that this dust cover is kind of mantling the underlying topography. And they source not from kind of one place, but often from the crests of places or little knobs where it's locally steeper. Here's another image of slope streaks. And one of the interesting things about this image is that you can see at the tops of some of these slope streaks here on this kind of left bunch, they're coupled with little dark halos. And you may not see it well in this projected image, but there are tiny little impact craters, fresh impact craters at the tops of these guys with these little dark halos. And we believe that those fresh impact craters are the ones that initiated these couple of these slope streaks. The other thing that you can see in this image is there are these dark slope streaks in the middle, and you can see that they have this kind of longitudinal ridges or features in them, which could be one of two things. They're either flow features from when the slope streak was moving, kind of left in the flow surface, or it could be that they're, again, scars from previous slope streaks. So, for example, you might be able to say, here's kind of a triangle. Maybe this area right here was a slope streak from before that got overprinted by one that came down later. Yes?
How true is the contrast in an image like that?
Good question, Kevin. So these dark slope streaks are, of course, these images their contrast stretch is turned up very high so that you can see the difference. The actual albedo difference between this dark slope streak and this respectively light-toned surrounding unit is only about 10%. So if you were actually standing on the surface, it wouldn't look like a big black channel in front of you. It would be probably be very subtle, and you might not even notice it. But we turn up that contrast pretty far to bring out other details. In addition to this, so you can see these features in it, which may be from a couple of things. You say, I can kind of see those features over here too on the right-hand side of this image, but that's because there are old slope streaks over here, which you may just be able to barely see, that are sourcing off steep areas over here on this crater at the upper right-hand side of the image. Here's an example of light-toned or bright slope streaks, and again, this view shows that at the apex of these light-toned streaks, there are tiny, perfect little craters at the tops of them. The freshest craters anywhere in this image. Although these slope streaks may yet still be quite old.
What are their diameters?
Oh, well, let's see. The scale bar there is 50 meters. Those diameters are probably, 3 meters? 4? I don't know. I haven't measured them. Something in that area. Very small. Yes. But these craters don't have dark halos around them anymore. So they're probably kind of old. You can kind of look and you can kind of see some, a little bit around it that's almost lighter tone than the surrounding unit, but they're not the very fresh, dark splotch. Other slope streaks, and also let me go back to this image. Also, you can see that these slope streaks also kind of excavate and they show a different texture than the surrounding surface. So this image, and I apologize for it being kind of noisy, this image, the reason why it's noisy is that HIRISE has really quite good signal to noise, and this image is taken in a shadow, and so that's why it's kind of noisy. But one of the things that it shows is it shows you this dotted line kind of going diagonally across the image with slope streaks coming off of it. And the hypothesis here is that a rock or block either got dislodged from an outcrop above or got thrown this way by a small impact and got some velocity transverse to the down direction and rolled down the slope here, setting off slope streaks as it went.
Hey, Ross.
Yes.
You can also point out that was taken about the time of the dust storm. So
Oh, yeah, this was...
That kind of affected all those images taken at that time.
That's right. This is coming up into that dust storm area from last summer. So yeah, that's going to affect some of the noise too. But yeah, this is right smack in the middle of a big shadow, which is probably more of it because there's other stuff that you can see that's not in shadow in this image. It's a little better, but the dust storm doesn't help. Here's another image. Here's a fresh little crater. There's little craters in there, but again, you can see this big dark halo around it in this image on the left, which is zoomed out. And on the right, this inset image is from about here, and on each one of these little slopes and surfaces, you can see, I hope, little dark streaks sourcing from the ridges. And the hypothesis here is that this impact hit, and the shock wave caused a bunch of dust that was metastable on these surfaces to avalanche down into slope streaks. This slope streak is a slope streak that was the subject of the Phillips et al. Paper from last year. And it's actually just the very distal edge of this slope streak. It's gigantic and has lots of great features. But one of the things I want to show you with this slope streak is that, again, the surrounding surface has this network of reticulate ridges, little presumably aeolian features. It shows, again, that along this edge that the slope streak is excavating. So this is high and this steps down. And yet at the distal ends of the fingers, you can see that I hope you can see, and if you can't, you're welcome to come up and look closer, that material seems to be piling up at the distal edges. And in fact, here you can see a kind of a crater here, and you might be able to see a bit of a pile up in the downstream side. And also, off the edges of the crater, there are these light-toned streaks, which are, in fact, remnants of this dusty material. If you look closer, you can still see this reticulate pattern on top as the flow left those kind of streamlined islands in its wake. The other thing is that, again, you can see these linear longitudinal ridges, and the possibility is that they kind of line up with the digitate parts in between the fingers. Kevin?
Yeah, I think I missed this. What is the slope?
The slope of the surface?
Yeah.
That's another interesting question. You're full of them. The slope itself are usually less than the angle of repose, so generally between 15 25 degrees are the slopes that we find slope streaks on. However, where the slope streaks initiate from their apexes are often steep knobs. So in the dry model, the idea would be that even though this material can't flow on the surface of that slope, that from a steep knob or a steep part it triggers and it falls and it gets some momentum to carry it down the slope. Yes?
What material is it?
It is most likely the very fine micron-sized Martian dust.
So the idea is it's completely dry, nothing but really dry dust grains.
That is one of the hypotheses, yes. Yes. And there are also wet hypotheses or lubricated flow hypotheses that I'll get to. There are an awful lot of slope streaks. We believe that we can that we can explain all of the observations that we see, including the ones I've shown you, with a dry hypothesis initiated by steeper slopes and things, momentum flow, very similar to avalanches and snowpacks. The angle of repose issue, the angle that the slopes are on, is a troubling one. With dry stuff, shouldn't necessarily be able to flow over great lengths on them. So that's an issue, and so wet hypotheses are not ruled out. They're still very much in play. I'm trying to think if there's any others. I was talking about these linear ridges, and they seem to be where digitate fingers are interacting, kind of in the webbing between fingers, if you will, and kind of going back upstream, and these others are kind of in those places. Although I was speaking with Misha Kozlovsky last week, and he said that he didn't think that was possible, that he'd done some reading on some avalanche stuff, and that they don't see those kinds of morphologies in dry avalanches. So maybe that's not what they are, and that's just coincidental.
Do you want to point out the perpendicular ridges too?
Oh, yes. So also, thank you, Cynthia. So also in the slope streak, you can see a couple of places where there are ridges here that are kind of across the stream, if you will. They're perpendicular to the direction of flow. And those features are not seen in areas outside the streak. And so one of the things that the Phillips et al. Paper demonstrated or discussed was that these are also probably features of the flow, that they're remnants, or they're kind of maybe similar to bars in fluvial systems. But they're places where, as the slope streak is avalanching and excavating stuff at the apex, in places not only at the toe, but in places upstream of the distal edges, it deposits these little mounds as well. And again, this was visible in the mock image, but only because this is a big streak and we think that it's in very deep dust. And so we can see the features just barely in mock, and certainly a lot better in HIRISE.
What kind of work relief are you seeing? How deep are these?
We think that the depth of this kind of step down is probably on the order of a meter. Pretty small. And so again, that's why an imager that takes pictures at a resolution of 5 or 6 meters per pixel just can't see any topography difference at all.
How big is the dust layer?
Here we think that
Dust layer, are you essentially excavating the dust layer to get something underlying, or are you...
Yes, that's what we think.
And how fine is the dust? Is this fine enough that it could be suspended in the atmosphere? Could the atmosphere play a role in lubricating the flow?
It certainly could. There's a Sullivan et al. Paper, the initial kind of Sullivan et al. Paper from 2001 on the mock observations that talked about, not only you're getting stuff that's moving, but you're also kind of getting atmospheric stuff.
You can have something like a paraplastic flow, except it's not a paraplastic flow.
Right, exactly. And in fact, that was one of the explanations for why mock didn't see any pileups at the distal end, perhaps, is that the dust just kind of went and it just kind of lifted up at the end. And so that's maybe a reason why you wouldn't necessarily see deposits at the foot. So let me talk a little bit about streak albedo. All of these facts are from a good review paper by Shurikofer and Harrison last year. Their work had a great survey of slope streaks from the Viking era to the mock era, and also a comparison of slope streaks between the beginning of the mock kind of time period and the end of the mock time period. And what they found is that whenever a new slope streak is observed on a slope, it's always dark. It's always a dark slope streak. And when a new slope streak occurs on a hillside with other existing streaks, the new streak is always the darkest in tone, and the older slope streaks are lighter in tone. Their work indicates that dark streaks have a tendency to fade over time. They saw dark streaks from Viking fade in mock, and a little bit of fading between early mock and later mock. And so the timeline that there's an evolution to these slope streaks, such that new slope streaks are dark, like the images I have here at the bottom of the slide. They're dark. They reveal they have sharp sides as they excavate or move material. And that as time goes on, airfall dust deposits on these slope streaks, and they begin to fade away. And then ultimately, there's an optically thick layer of dust on top of them, such that you don't see them at all. And those of you in the back probably can't see them at all. And those of you in the front can see enough to see these excavation scars, and that's the only remnant of their existence. And as I said before, there's this issue of, so that works great. If new streaks are always dark and they fade away, that's awesome. But what about bright streaks? That's always been kind of an issue, a fly in the ointment in many of the formation hypotheses of slope streaks, is where do bright slope streaks come from? And it'd be one thing if bright slope streaks were, if you had a hill and it had bright slope streaks and you had another hill that had dark slope streaks, you might be able to say, oh, there's different kind of stuff that's being excavated or being revealed. But we find slopes where there are both bright and dark slope streaks on the same slope with the same orientations and aspects. So another item from this review paper is that bright streaks are probably older, meaning that no new observations of them were seen. And a hypothesis, although not really tested in any way, is that perhaps the dark streaks turn into bright streaks. And there's one observation where this paper had a Viking-era slope streak that was dark and a mock-era slope streak that had turned bright. Yes? Okay.
So we're talking about albedo changes on the order of years. Would that be a correct inference?
Probably tens of years, if not longer. Yeah.
Although you can see theta in less than that.
That's true. That's true.
It's subtle, but yeah.
Right. And that's the problem. Since these imagers aren't absolutely calibrated, it's hard to compare DN to DN and determine how much exactly.
So it's in quantum
Not necessarily.
I've just been given some information.
Oh. Okay. Yes.
I saw a slope streak that was dark at the top and light at the bottom.
Yes. Yes. We also have some where they change in the middle. So what I'm going to do is I'm going to try and put forward some explanations for that don't have anything to do with material properties, but have everything to do with photometric properties for how slope streaks might possibly change from dark to bright. So the hypotheses I'm going to present to you, as I said, are based entirely on surface morphology differences of the dust between the streak surface and the surrounding surface. These hypotheses assume that new streaks are dark. You may choose your favorite reason for why they are dark. They could be wet, staining, or wicking. They could be dry, just simply indicating that a larger grain size has been exposed or microstructure properties have been changed during the flow. But they're dark. We'll assume that they're dark. We'll let other people worry about why they're dark. And that they, in fact, move material. We'll also assume that average albedo dust over time settles onto the streak surface. Okay, so those are our givens as we go in. So the first one here is that these might become bright due to the removal of surface roughness effects. So the model goes as such. So again, I hope you'll notice in this example image that the surrounding surface here has this network of reticulate ridges. They're isotropic. They don't have a preferred direction. And when a slope streak avalanches, it reveals this fresh surface, but that surface is also smooth. It doesn't have this network of ridges like the surrounding surface does. And it's dark. Over time, light tone particles are blown into the streak, and they eventually cover it with an optically thick layer of dust. The same albedo stuff inside the streak as outside the streak. The only difference is that outside the streak there are these ridges, and inside the streak this layer of dust is conformable. It's smooth. And Hapke theory tells us that rough things are darker than smooth things. And so even if you were to go out to the slope streak and take a shovel, the shovel of stuff from inside the slope streak and the shovel of stuff from outside the slope streak would have the same, if you just looked at the particles, they would have the same albedo. But since the dust outside is in these ridges and the dust inside is smoother, the observed brightness is different. And eventually, inside on the slope streak, over some time period, a network of ridges similar to that outside finally forms on the material, and the streak appears to just fade away. Then we'll have the same observed brightnesses as outside. So that's one hypothesis.
So wouldn't you see contrast reversals then if you looked at these at different phase angles? Wouldn't that be a way to study it?
No, because different you wouldn't from different azimuths because they're isotropic.
Right, but different like lighting.
Right.
Sun.
Right, and the problem is that with most of the imagers that we use on Mars, the phase angles are not wildly different. That could be a way to do it if we were allowed to roll at very large angles, but then you have more atmosphere and there are other complications. But that certainly is a way to go about testing that.
And the different sun angles aren't enough to create brightness differences.
Different sun angles? Different solar, you mean different?
Or is it otherwise just the same?
Yeah, at these scales, it's not wildly different. And since this topography is, tens of centimeters to a meter, on top, the difference is not very large. The other hypothesis, which is maybe equally crazy, is that, as I mentioned, some of these slope streaks have these longitudinal ridges. Not all of them do. And again, the idea would be that when the slope streak forms, it forms with these ridges, as we saw in other images that I showed you earlier in the talk, and the darkness of a fresh streak dominates the contrast. But again, over time, dust gets deposited, and then eventually you have the same dust, again, in the streak as you do on the surrounding surface, but these linear ridges then could possibly act like a bank of reflectors. Since they're linear, they have a strong linear trend, and if the sun is shining perpendicular to them, or even off at an angle, you'd have a cosine dependency, they might reflect slightly more light, and so they might look a little brighter. Now, as I had mentioned in answer to Kevin's question before, dark-toned slope streaks are only 10% darker than the surrounding surface. Bright-toned slope streaks are only like 2% brighter than the surrounding surface. So it's really not that much. And again, under this hypothesis, these streaks the bright streaks would only turn dark if there was enough dust to actually bury the ridges. But again, in this example image, there's kind of a surrounding texture, and so this may well be not at all what's happening. It may simply just, again, be another example of the first hypothesis, and the ridges are totally incidental.
Ross, didn't you say previously that if it was you argue that if it was rough inside the streak, it would be darker, and then now you're saying that there's these ridges, and so it's brighter?
If
What's
it's
the difference? Is the difference that here that it's like coherent scatter?
yeah, since these are in the previous hypothesis, since this network of topography is isotropic, and in this ridge idea, they're linear and they're aligned. They provide a uniform reflectance. But I agree, it's kind of crazy, and I'd be happy to be proven absolutely wrong. And again, this hypothesis requires a fair amount of photometric modeling that I haven't yet done. This is just kind of back of the envelope. How could you make things bright based on some of the observations that we saw? And so in summary, the topographic relief that we see in HIRISE indicates that mass has moved down slope in slope streaks. The models which invoke only staining, wetting, or wicking, and not particle movement are not supported by these observations. Now, let me caveat that with the fact that much like Mach saw no topographic relief, HIRISE sees some. There are certainly some slope streaks in which HIRISE doesn't see any topographic relief. Now, those slope streaks could equally be explained by wetting, staining, or wicking where no particles are moved, although the position of a Chuang et al. Paper that I was a co-author on, the HIRISE team, is that those slope streaks are simply in a dust, are excavated in a dust layer that is too thin for HIRISE to resolve, just like some of these were in dust layers and excavated depths which were too shallow for Mach to resolve. And from our observations, we think that dry dust avalanches seem to fit best the most of the observations. But we certainly can't rule out, as I said, all possible wet models, and there are certainly some very good ones that remain. And Misha Kozlowski will be presenting a poster at LPSC this year that talks about a very excellent wet model hypothesis. And also, I showed you there are several possible triggering mechanisms for this dry avalanching possibility. And finally, that streaks are part of this continuum of mass wasting features from all depths in this dry dust. And that bright slope streaks are not a different, strange population that has to be shoehorned into theories of dark slope streaks, but that there's a possibility that they're a likely pathway for some slope streaks to get bright and then fade, although many slope streaks are probably don't ever go through a brightening. Thank you.
Before we get to questions, let me just say I forgot to mention one thing in the introduction. Ross is available for lunch, so during the question and answer, think about whether you want any further discussion with Ross, and just stick around and join us for lunch if you do.
Thank you.
I want to ask you about this solar radiation effect on these nano-sized particles.
Okay.
I would assume that there would be some kind of ionization or electrostatic charge that may build up that would allow you to create those avalanches or lubricate them.
Oh, like electrostatic dust lifting,
Right.
kind of. Yeah.
And possibly also account for some of the difference in colors, since what you have underneath is less electrostatically charged, whereas the outside would be still charged.
And how would that... So in answer to the first part of your question, there certainly have been papers hypothesizing those kinds of mechanisms. I'm not electrostatic dust charging expert, so I can't answer your questions on that front. But I have a question for you. When you say that might account for color differences, how would it do that? Is it a compaction thing?
I don't know. I'm thinking polarization, but
Okay.
I'm no scientist at all.
Okay. I don't know, but that might be interesting to look into. Yeah.
At the beginning, you showed that the dust looks like originated by small impact.
Some of them. Mm-hmm.
But around it, there were also larger impacts that were not apparently related to any dust.
Large impact craters?
Yeah, the
right.
larger ones. So how you explain it? Is it...
So one explanation would be that those larger impact craters were in place long before in the geologic history, and only after they were in place did a thicker layer of dust mantle get in place, and then the more recent small craters were the ones that disrupted it. Those big craters were already there when the dust mantle got put down. Bob?
Ross, could you say a little more about the wet models? Presumably water is involved. What's the source? What is it growing? That sort of thing?
Those are great questions, Bob. No one seems to know. The models indicate, so there are some models early on that indicated there was some sort of water table. Some of these slope streaks were seen to kind of source from a similar layer, but that layer I think is just where it was steepest. And certainly I can show you places where on a slope, they come out at a bunch of different places, although that was an early hypothesis for where the water came from. There was some sort of aquitard there. The best wet models, again, the Kraslovsky one, poses that there's kind of just underneath, that the surface dust layer isn't, and I'm probably getting this wrong, but the surface dust layer is enough to provide some sort of insulation that you get some kind of permafrosty stuff below that. And during seasonal cycles, it gets warm enough to kind of melt that permafrost into something that's liquid that percolates down to the base layer, wets it, and then may cause slippage on the dust. But I would recommend you to those papers for a little more details. Continue.
Hi, Ross. Did you look at any of the high-rise stereo that you didn't comment on? I'm just curious, are there none, or because we have tons of stereo?
There are. There's in fact a stereo pair of the biggest, that wishbone slope streak, the big one. I haven't made an anaglyph of it yet. I need to. And I think that it's in the queue, on the big queue of to make DEMs of, but I don't believe that one has been made of slope streaks yet.
And the other question was, do you care to comment on? You didn't show some of the neat ones that have anastomoses.
Oh yeah, no, I went past a lot of things that are interesting about slope streaks, to be sure. There are slope streaks that do show anastomosing patterns where they hit a topographic obstacle like a hill and they go around it and then join back up. Again, that's hard to explain with purely dry hypotheses. That's something that we often see in wet or fluvial features. So it's a fine question. And it may be that the dust and the electrostatics may be doing strange exotic things, or it may be that that's a very good reason for them to be wet or lubricated flows.
You just mentioned the word electrostatics.
Yeah, I did, again.
What could be the role of a sudden burst in surface charges of the same polarity that would change the adhesion between the different grains as they start moving until that charge is exhausted, then the whole thing would settle?
Yeah, that might provide, the electrostatic argument might provide the impetus, might allow you to explain how these movements, these dry mass movements, move on less than angle of repose slopes. But I don't know that anyone has done the detailed modeling to prove or disprove that yet. Absolutely. Does that answer your question? I don't know that it does.
Yeah, could there be some experiments being done that would?
I don't know. I'm not familiar with people doing experiments on the dry stuff. You certainly could do it.
I know John Marshall has talked about that. I don't know if he's actually done any experiments
Okay.
on that.
I think it'd be hard to get the right pressure, temperature conditions, and then get the right grain size and stuff. Richard?
What's the global distribution of slope streaks, and is there any pattern between, like, has anybody looked at any correlation between them and where GRS has actually occurred?
The answer to the last question, I think, is yes, and I think it's not a complete overlapping set. Slope streaks are found in regions of high dust cover, which is on Mars is kind of mostly equatorial around the Tharsis volcanoes and in Arabia, Terra. But they kind of occur in other places as well sporadically, but that's where their greatest concentration is. What?
One thing you didn't address that I noticed anyway was, could the darkening of the slope streaks have anything to do with oxidation or some sort of space weathering of the material underneath the surface?
Oxidation of the, or weathering of the exposed stuff or of the overlying stuff?
Whatever's been exposed.
You mean making it dark or making it bright?
Either.
Okay, well, as I mentioned, since we've seen new slope streaks that are dark in less than 20 days between, it doesn't seem like there'd be a lot of time for a slow space weathering kind of process, unless I misunderstand how it works. And it seems like the oxidation I'm not as familiar with. That could certainly be something that happens, or something that happens subsurface, and the bright stuff gets washed away, and you're left with something that's spent some time covered up and being altered, that then gets rained back down on by surface stuff. As far as changing color, as far as fading, again, I'm not as familiar with the processes, but it seems like it's best explained by dust from the atmosphere settling on top of it. But that could be wrong too. Okay, well, great. I've taken up my hour. Thank you very much for being patient and answering questions.
And one other thing that I missed in the introductions is that we actually have a colloquium this coming Friday as well. Paul Gazis and Trion Levat will talk about their great tool for analyzing multispectral, multivariate data sets. So come Friday at noon to hear about that. And stick around if you want to have lunch with Ross.
Great. Good talk. That's fun. Can you have a copy of your PowerPoint? Absolutely. Thank you. So you mentioned you want what format you want in? PDF, PowerPoint, whatever.